probability and statistics. Here the content is sampling theorems, basic definitions of probability, events, definitions, all these things, mean, median, mode, and distributions, random variables, and binomial, Poisson, normal distribution. These are the contents in probability and statistics. Okay. So first I am recalling the basics what we have learned in plus 2 level 12 standard BTech first year. That means that definitions are also available in your material or any standard textbook. If you refer, you can easily understand. Okay. I will tell you the points to write means that are important points. Sometimes they are not available in some textbooks also. All other points what I am going to explain now, they belongs to any standard textbook or your material also. Please check. Okay. So there are two things: uncertainty, certainty. Certain means 100% happened, sure. That is also called sure, S-U-R-E, sure. That is certain event, that is 100% happened. But we consider in probability uncertainty. That is in probability we studied the uncertainty, that is happening so and so, not exactly. Okay, or exactly like that. Okay. Not 0%, not 100%. That means somehow only, okay, maybe or may not be, like that only. 90%, 50%, that is uncertainty. That is, okay, not completely 100% or 0% like that. Okay, failure or success. Success, completely success means 100%. Completely failure means 0. Okay. Now, in this first definition is random experiment. A random experiment is an experiment in which three conditions are satisfied. First condition: all the outcomes of the experiment are known in advance. What is the meaning of all the outcomes of known in are known in advance? Suppose if you are seeing a game, that is, or if you are playing a game, that is tossing a coin. So before starts the game, that is before playing that tossing a coin, we should know total outcomes. That is, what are the outcomes in tossing a coin? Head and tail. So that is, all the outcomes are known in advance before beginning the game. Second condition: once we perform the experiment, the outcomes are not known in advance. That is, suppose if we toss a coin, before that only we cannot say that is it is exactly head, it is exactly tail, like that. The outcomes are not known in advance. Okay. Once we start to play, that is experiment, it means the experiment results an outcome that is not known in advance. Next, third condition: the same game can be repeated any number of times under identical conditions. So whatever the conditions you are keeping in first time of playing a game, if in the second time of the same game, third time, you keep the conditions constantly, that is called under the same identical conditions. The experiment can be repeated under the identical conditions. Okay. See, what are the three conditions? The set of all outcomes are known in advance before beginning the game. Once we start the game, it results in an outcome, that is the outcome not known in advance. Okay. Next, third condition: the experiment should be repeated under identical conditions only. Next, the performance of the random experiment is called a trial. Okay. The result of a trial is called outcome. Next, the collection of the set of all outcomes of the given game or of the given random experiment is called a sample space, denoted by S. Okay. What is outcome? End result of the trial. Okay. Next, so S, or in some textbooks it is denoted by omega. For example, for tossing a coin, what is sample space? Either head or tail. Don't say either or. What are the total outcomes? Head, comma, tail. Head stands for H, tail stands for T. Similarly, for tossing a coin twice, or the same also can be written as two coins tossed once. In this, both are same. S is equal to, once you remember the one coin game H comma T, in the second position of each outcome in this, add H and then tail. That means H H, HT, TH, TT. So here n of s is equal to how much? 2 power 1. In this, n of s is equal to how much? 2 square. Like that, if a coin is repeated 3 times or 3 coins tossed one time only, a coin is tossed 3 times or 3 coins tossed at one time only, the same having, that means both are having same meaning, then hence n of s is equal to 2 cube. So like that, if a coin is tossed n times, the total number of outcomes, that is n of s is equal to 2 power n. Okay. The same coin game can also be asked a true false question. One question can be attempted in how many ways? Options true, false, that is 2 power 1. That if there are 2 questions, these 2 questions can be attempted with the true false questions in how many ways? 2 into 2, 2 square, true true, true false, false true, false false. The same language can also be compared as 0-1 language, 0-1, 1-0, 1-1, 0-0, like that. Okay. Next, for throwing a die one time, comma, s is equal to 1, 2, 3, 4, 5, 6. 6 outcomes. So n of s is equal to 6 power 1, 6 raised to 1. For throwing 2 dice once, each die one time, or die is thrown 2 times, same meaning, comma, n of s, first of all, s is equal to, in the first outcome here 1, in the second position 1, 2, 6, that means you will be getting 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Similarly, if the first place 2, the second place can occupy 1, 2, 6, gives 2, 1, 2, 2, so on, 2, 6. Like that, 3, 1, 3, 2, so on, 3, 6. 4, 1, 4, 2, so on, 4, 6. 5, 1, 5, 2, so on, 5, 6. The last one is, if the first place 6, then the second place takes either one from 1 to 6. That is 6, 1, 6, 2, so on, 6, 6. So from this, n of s is equal to how much? 6 square, that is 36. Similarly, if a die is thrown n times, the total number of outcomes, that is n of s is equal to 6 raised to n. Okay. Similarly, a game containing throwing a die and tossing a coin. That means tossing a coin, 2 outcomes, total outcomes. Throwing a die, 6 outcomes. The total number of outcomes at a time playing the game as tossing a coin one time, throwing a die one time, which gives 6 into 2, 12 outcomes. H1, H2, H3, H4, H5, H6, T1, T2, T3, T4, T5, T6. Next. In a leap year, that is 366 days, it has 52 weeks completed, and the remaining 2 days are in the following ways. Leap year 366 days means 52 weeks plus 2 days extra. The 2 days are in the form of Monday, Tuesday, Tuesday, Wednesday, Wednesday, Thursday, Thursday, Friday, Friday, Saturday, Saturday, Sunday, Sunday, Monday. That is 7 total cases. Okay. Similarly, non-leap year, that is 365 days, that means 52 weeks plus 1 day extra. That 1 day is of the form either Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. So in that leap year, non-leap year question also, the total cases is equal to 7 power 1. Okay. Next, in a pack of well-shuffled cards, 52 cards are there. In that 52 cards, 4 suits. The name of suit is also called design. Design means 4 symbols there. Spade card, spade symbol, heart symbol, diamond symbol, club symbol. Each is of 13 cards. So there are 4 suits. 4 into 13 is equal to 52. 2 colors, red color, black color. Each color is 26 cards. Next, face cards. So what are face cards? King, queen, Jackie. K, Q, J. So each is of 4 cards. So how many face cards? 4 into 3 is equal to 12 cards. Honors. In a pack, there are 4 types of honors. A, ace. K, king. Q, Queen, J, Jack. So that is 4 into, each is of 4 suits, 4 into 4 is equal to 16 honors. Okay, please remember this is pack of 52 cards, leap year, non-leap year, and these two coin game, dice game. These are the regular games in probability generally. Okay, there are many games. Next, see, NPR is equal to n factorial by n minus r factorial. Okay, and NCR is equal to n factorial by r factorial n minus r factorial. The meaning of NPR is it is a permutation taking r things arranged from the total of n things. That is, total n things are there, but we are taking r things and then arranged. The number of such arrangements is called number of permutations given by NPR. From the given total n things, we are selecting some things. R things selected from the total of n things is called combinations or selections, that is given by NCR, n factorial by r factorial into n minus r factorial. Okay, so NP 0 value 1, NP 1 factorial n, without factorial I am explaining, NP2 value n into n minus 1, etc. NPn value n factorial. In this, NC0 value 1, NC1 value n, NC2 value n into n minus 1 by 1 into 2. Okay, NC3 value n into, the way of evaluating, because some people they forget all the basics also, due to that only I am explaining, 1 into 2 into 3, so on, NCn again 1, 1 into 2 into 3. Sometimes NC are useful by NC n minus r. For example, if you evaluate 9C8, whenever the numbers are near to each other, short to each other, then this formula helps a lot. 9C1 value 9. So the suffix indicates that number of terms present in numerator and denominator. For example, 2, here suffix 2. 2 numerator terms, 2 denominator terms. Suffix 3, 3. Like that, suffix 8 means it is, first of all, takes lot of time writing 8 numbers in numerator and 8 terms in denominators. In such cases, this formula helps a lot. Whenever n and r shorter to each other, near to each other, then this is the suffix indicates, suffix, then the latest second suffix is obtained by difference of n and r. Okay. And these combinations I have given in 10th class also, in 11th standard, Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Just refer that basics. Okay. Next, event definition. So event is a set which is containing some outcomes. All outcomes belongs to the sample spaces. That is, event is a subset of the sample space. Event also containing some outcomes. Suppose if I define event A is equal to sum of obtained numbers is 8 on throwing a die 2 times. You know, a die is thrown 2 times, that is n of s is equal to 6 square 36 outcomes. In that 36 outcomes, you collect outcomes whose sum of the obtained numbers, each position in that n of s 36 outcomes, each outcome is, first position is showing a number on the first die, second position indicates showing a number on the second die. Obtained numbers means whatever the number showing once we throw a dice or pair of dice. Okay, 2 dice. So in that, which outcomes whose sum corresponds to 8? 2, 6. There is no 1 plus 7 is also 8. 1 comma 7 don't consider in this set because 7 is not a phase in any die. Okay. 2, 6, 3, 5, 4, 4, 5, 3 and 6, 2. Only 5 favorable cases if I define like this. Similarly, depending on the event, that is depending on the sentence of your problem, you properly named as A, B, capital E, capital E1, capital E2, and some problems you have to find like this, that it gives number of elements in the event, then only probability we can define. Okay. Now, probability of an event is denoted by P of A, or probability of an event E is denoted by P of E. Okay. Which is defined as m divided by n, which is a fraction, where m is the favorable cases to the event A happened out of n equally likely cases. That is total cases, total equally likely cases in the game is n. Out of n cases, m values, m outcomes are favorable to the given event A. Then probability of that event is defined by m by n. Okay. So clearly 0 less than or equal to P of A less than or equal to 1. Because suppose for some events, suppose see, if I ask the question, sun rises in the east, sun rises in the east, that is always happened. So that's why its probability is 100%. So, and sun rises in the west, that is never happened in throughout the world. Okay. So that's why probability sun rises in the west is 0. So generally that whenever the probability is not happened, that is probability 0, that event is called impossible event. Next, once you get the probability P of some event is equal to 1, that event is called sure, S-U-R-E, sure event or certain event. Okay. On which no importance given, on which no importance given in the probability. Whenever P of an event, probability of event is equal to 0 or 1, no importance given. That means we are discussing the problems strictly lies between 0 and 1. But in some problems you may get probability 0 or 1 also. Okay. But no importance given. So P of A is equal to 0, then A is called impossible event. Similarly, if P of A is equal to 1, then A is called certain or sure event, on which no importance given in these two cases. So that's why we consider 0 less than probability of any event less than 1. Okay. Uncertainty. So whenever probability 0, impossible event, probability is equal to 1, certain event on which no importance is given in the theory of probability. That's why 0 less than P of A less than 1. Next, A dash or A power C, A complement, in some textbook it is A bar, which is called the event A has not happened. Event A is not happened, denoted by A dash. So here out of total n cases, m outcomes are favorable to the event A. What about other outcomes? N minus m outcomes, which are not favorable to A, but they are favorable to the event A dash. So P of A dash is defined as n minus m by m. N is the total cases in the game. M outcomes are the favorable to the event A. Automatically remaining n minus m outcomes are favorable to the event A dash, because A dash or A complement A bar is called the not happening the event A. So its value is 1 minus m by n. M by n I already denoted, given by P of A. Therefore P of A plus P of A dash is equal to 1. Probability of success plus probability of failure is always 1. Here P of A dash is nothing but 1 minus P of A. This is the basic rule. Next three definitions are equally likely events, mutually exclusive events, exhaustive events. Let us start with two events. Two events A and B. Two events A and B are said to be equally likely if one of them cannot be expected to happen in preference to other. Similarly, three events, four events. No preference to happen in one another. Okay, that events are called equally likely. Suppose when tossing a coin, probability of head will not happen to prefer to other, or tail will not happen to, that means no importance given to happen in preference to other. Probability of head is nothing but probability of tail. Equally chances, they are having equal chances. Okay, next, mutually exclusive events. Similarly, start with here two events A and B. Two events A and B are said to be mutually exclusive if they are disjoint. That means they have no common path according to set theory. Next, that is that they cannot occur simultaneously. That means when tossing a coin, head and tail cannot happen simultaneously. Either head happens or tail happens. Okay. Exhaustive events. Two events A and B are said to be exhaustive events if both A and B include the total possible outcomes of the random experiment. That means both A and B includes all the outcomes of the sample space. That is A union B is equal to yes. Whenever A union B is equal to yes, the two events A and B are said to be exhaustive. Whenever mutually exclusive in set theory, A intersection B is equal to 5, disjoint. Whenever the two events whose intersection is equal to 5, then A and B are said to be exclusive. Whenever two events A union B is equal to total all outcomes sample space, then the A and B are called exhaustive events. Equally likely means equal chance, I told you already. Okay. Next, one more point you remember, complementary events. Whenever two events A and B is satisfying, A union B is equal to yes, A intersection B is equal to 5. That is both exhaustive and exclusive. These two words in some textbooks it is also called complementary events. Next, addition theorem of probability. Let A comma B be to any events in the sample space yes. Then P of A union B is equal to P of A plus P of B minus P of A intersection B. How to remember? Just like number of elements in A union B. First collect singleton sets A, B, whose symbols are positive, pre-symbols. After the collection of all singletons, then what is your next stage? Collecting double sets, possible double sets. That is A intersection B, only the possible double set from A comma B. Whenever you change the nature, single to double, double to triple, then you also change the symbol, pre-multiplication symbol. Here first I started with single sets with positive, double sets at a time, A intersection B with negative. If you go for next category, next nature, triple sets, then you change the symbol of previous one. Okay. Similarly, P of A union B union C. Here three sets I have considered. First collect all single sets whose symbols are same, positive, P of A plus P of B plus P of C. Now after the completion of single sets, then your next step is collecting double sets, collecting all possible two sets, AB, BC, AC. So here nature changes. That's why plus changes to minus symbol. Minus, easy to remember, that I am telling these logics to remember easily without by hearting. P of A intersection B minus P of B intersection C minus P of A intersection D. After all double sets, then your next nature is collecting triple sets. Out of 3 sets, there is only one triple set, that is ABC, A intersection B intersection C. Because we are changed the nature, now similarly change the symbol. Minus 2 plus, that is plus P of A intersection B intersection C. Like that we can write this theorem into 3 sets, 4 sets, 5 sets also without by hearting. Okay. Next. Note. P of A greater than or equal to 0 for any A subset of S. 2. P of A1 union A2 union so on union AN is equal to P of A1 plus P of A2 plus so on plus P of AN, comma, if A1 A2 so on AN are mutually exclusive. So whenever the events are mutually exclusive, that is according to set theory, the events intersection is equal to 5. So whenever A intersection B is equal to 5, probability of 5 is equal to 0. So according to addition theorem, now this result becomes sum of their probabilities. That is, whenever the events are mutually exclusive, probability of their union is equal to sum of their probabilities, because no common path, that is, it gives common path gives 5, probability of 5 is equal to 0. Probability of sample space is always 1. Whenever a set function, probability set function satisfying these 3, that is, whenever a function satisfying these 3, that is called probability set function or probability axiomatic approach. Next here, probability of A intersection B dash. This is also read as in set theory only A. This is obtained by probability of A minus probability of A intersection B. Just remove the common part from A. Similarly, probability of A dash intersection B. This is also in sentence verbal descriptive read as only B. This is defined as probability of B minus probability of A intersection B. Just I am giving 2 Venn diagram. A is a circle, one set, B is another set. This is A, this is B. Sample space rectangle. So here, just I am shading this type of, say, shaded part 1. This type of shading, say, 2. This type of horizontal shading, say, 3rd part. Let us say the outside the circle's 4th part. Part 1 is nothing but only A. Okay, that is in set theory it is A intersection B dash. Part 2 is nothing but only B. These are just Venn diagrams, set theory only. Sometimes while doing problems it is useful. A dash intersection B. Part 3 is nothing but common part A intersection B, that is both. Part 4 is nothing but neither A nor B, that is A dash intersection B dash. Neither A nor B, empty region, nor B. And sometimes you remember De Morgan laws also. A union B whole dash is equal to A dash. Well, these all these points, sometimes while doing the probability problems in simplifications, in some steps for simplifying, these are helps a lot. Okay, A dash intersection B dash, I mean, that is I already mentioned. A intersection B whole dash is equal to A dash union B dash. So both means intersection. At least one of A comma B means A union B. Please remember the verbal descriptive sentence equivalent set theory notation. Both A comma B, that is A intersection B. Only A means A intersection B dash. Next, at least one of A comma B means A union B. Exactly one of A comma B means, that is from A comma B only one of the events happened. That is, if A happened, B fails to happen. If B happens, A does not happen. Okay, so here I am writing exactly one of A comma B is nothing but, in set theory, if A success, then B not happen. A happens, B not happen. That is A intersection B dash. Other case, union A dash intersection B. See, exactly one of A comma B means collect all the possible cases. If A happens, then B does not happen. That is first case, A intersection B dash, set theory. Other case, or A does not happen and B happens. That is denoted by, in set theory, A dash intersection B. So once if you get more than one case, in each case followed by union. So two cases, two events A, B put together the symbol intersection. If that type of notations is more than one, so you apply union between every two notations. Each notation is in the respective possible case. What is the possible cases? Exactly one of A comma B means first case is A happens, B fails. That is A intersection B dash. Second case is A does not happen, B happens. That is A dash intersection B. So two possible cases here. In each case, you apply first intersection. So between every two cases, and then you apply union. That is. Similarly, it is useful for three sets A, B, C also. Exactly one of A, B, C. All A, B, C. A intersection B intersection C. At least one of A comma B or C. That is A union B union C. Like that. So all these helps a lot while doing probability simple problems. Next. So I am going to do one example. After that, four important definitions are there. Preference given to, first of all, problems on that four definitions. So in this first chapter, the preference given to problems generally in GATE 2. Conditional probability, independent dependent events, Bayes theorem, total probability. All these are basic level only. Sometimes 30 to 25 to 30% times problems given by, so far what I explained the basics. All other 60 to 70 or sometimes 80% problems given by the problems with Bayes theorem, total probability, independent dependent events, and next conditional probability. After one or two problems I am going to explain that also. Good evening to all. Today we are going to start the last day probability. We have discussed a few definitions along with one example, and we are continuing one by one definition along with GATE question problems. Okay. So the next one is conditional probability. let A comma B subset of S and P of A not equal to 0, then probability of B after the event A has occurred comma is called the conditional probability B given A, comma denoted by P of B given A. And is defined as P of B given A is equal to P of A intersection B divided by P of A. That's why we have assumed P of A not equal 0. Similarly, P of A given B is equal to P of A intersection B divided by P of B if P of B not equal to 0. See, A, B are two events in the sample space S, and we have taken P of A not equal 0. Then the probability of the event B after the event A has occurred, that is after the event means here two cases, first is happened, then we are finding the probability of second. So after the event A has occurred means A has already happened in the first time. Now the second time is going to happen, which is B. That is called the conditional probability of the event B given A. Given A means whatever the thing given, that is happened already first. Okay, the next thing whatever it may be, we are going to find the probability. That is the notation B given A, P of B given A, which is defined as probability of intersection divided by P of A. Similarly, this is probability of the event A, we are finding the probability of A given B. That is after the event of B has occurred, then the probability of A is called conditional probability of the event A given B, defined as intersection divided by probability of denominator, that is B. Taken P of B not equal 0 because denominator. One example I am doing. Example 2007, 2 marks given. An examination consists of 2 papers, comma, paper 1 and paper 2. full stop. The probability of failing in paper 1 is 0.3 and that in paper 2 is 0.2 full stop. Given that a student has failed in paper 2, comma, the probability of failing in paper 1 is 0.6 full stop. The probability of a student failing